Professor,
Yeah.
hi, good morning. Can I ask you a quick question?
Yeah, sure.
So
What's
when
up?
I went to do the homework, there was like like something about chapter one.
Okay. Did you have a question about the content or?
Was that mandatory to do, or I'm not sure.
Yes, the homework is mandatory to do.
No, not
Sure.
chapter two, the chapter one. It wasn't, it was just one thing on there, but it wouldn't let me open it. I guess I went out
Uh,
of the way.
yeah, maybe send me an email and I can take a look at it.
Okay.
Yep. Okay. Okay, so the plan for today is to finish section 2.5, solving equations with fractions or decimals. So this is actually kind of a longer section, so we'll probably see about as many questions in 2.5 today as we did last time. And then we have a shorter section solving a formula for a specific variable. So kind of implementing our strategy from 2.4 and 2.5 uh, when we have more letters, more variables in play. And then jumping into section 2.7, which maybe feels like it switches gears completely, talking about inequalities. But we'll see really the kind of tools and techniques are pretty similar to equations. So that is the plan for today. We might or might not get through all of 2.7, but we should at least finish up 2.5 and 2.6 today. The quote of the day today is kind of a comic. This is from XKCD Comics. They make kind of funny, like math, science, kind of related, or just generally kind of nerdy comics. And uh, this one goes, the guy on the left says, when a metric becomes a target, it ceases to be a good metric. And I think this is sometimes known as like Goodhart's law or Goodhart's law or something like that. Um, and essentially, the idea is that, let's say a certain company wants to maybe have better customer service or maybe get a larger market share or something like that. They have some kind of underlying goal that they want, and and they have some metric that says, are we doing good in this area? Are we doing bad in this area? But then if you take that metric and you tell people your job or your salary or your bonus or something is dependent on that number being good, they'll kind of they're incentivized to game the system, right? And people tend to respond to incentives, so um, they are likely to game the system and make that one number look good at the expense of the actual thing that it's supposed to be measuring, or even at the expense of the company as a whole, right? Um, and then so the other person says, "Oh, that sounds bad. Let's offer a bonus to anyone who identifies a metric that has become a target." Thus, you know, uh, thus creating a target out of metrics that have become targets. So people will identify all kinds of silly things and say, this is a metric that's become a target. Um, and one of the kind of classic examples of this, I don't know if this is real or apocryphal or whatever, but there's a bunch of different versions of this story from different countries. But it goes something like, some area has a big rat infestation and they need to get it under control. So they go out to the populace and they say, okay, if you bring in rat tail, we'll give you some amount of money. We'll give you, a few dollars for each rat tail you bring in, essentially as evidence that you've killed one of the rats in the infestation, and having everybody chip in to kill the rats in the infestation and giving them this very tangible incentive to do so. Um, Hopefully, we get rid of the infestation, right? That's the goal. But then people might figure out that the amount of money you're offering is actually cheaper for them, or they're able to breed rats, and maybe it's easier to breed rats than to catch the ones in the wild. And kind of ironically, the better you get at breeding rats, the more rats you get, and the better you get at catching the rats in the infestation, the less rats there are to catch, so it gets harder to catch the rats. Um, so maybe people start actually breeding rats and then killing the rats they bred and turning in their tails, right? So it's not really rat tails that we want to buy for $3. If we wanted a whole bunch of rat tails, that would work great. But it's that we created this metric that's not exactly the target, and people just found a way to game the metric. So maybe the rat population is still growing out of control. Maybe it's even getting worse if some of the the bred rats are escaping. Meanwhile, we're getting lots and lots of rat tails now. So we've incentivized turning in rat tails, not eliminating rats. So anyway, that is the idea for today. Kind of roughly speaking, be careful what incentive structures you create if you're a manager or even if you're a parent or something, right? When you say do this or don't do that, or there's a reward for doing this or a penalty for doing that, what incentive structures does that create? It always creates some kind of incentive, but often not the incentive that you think you're creating. And that's a fair argument with grades as well. We have this formula, we compute some number at the end, and we assign A, B, C, D, F, and this grade is intended to represent something like mastery of the course material. How well does it actually do that? That's something that our faculty are quite concerned with, and accreditors as well. So we constantly do this accreditation or assessment cycle. We're constantly assessing our courses and seeing if the feedback that we're giving students or the formal grades that we're turning in are kind of in line with what we expect them to be, if they're representing what we think they're representing, or if they're, I mean, we kind of know that it's a metric that's become a target. I mean, that's going to be how it is. The student's going to say, well, if I have a whatever 78 in this course, I'm going to work really hard to get 2 points, but not too hard after that, because I'm not going to go from a B to an A with only a couple weeks left. So we're certainly aware of that, and we try to be cognizant of that and make sure that what we're measuring is actually in line with what we want to measure. Okay, so jumping into 2.5, we're going to start right off with 2 exercises. So if you remember from last time, we had our general equation solving strategy. Let me actually jump back there and grab that to put it on the screen. There we go. And you can reference that while we work on these exercises. So we had our general equation solving strategy, which was the kind of previous section strategy plus clearing fractions or decimals at the beginning. So take a look at these 2 exercises, maybe take about, let's say maybe 7 minutes for these, and work through these 2 exercises. And note that in this first exercise, well, this is kind of a general strategy, but we might actually not want to clear the fractions in this first one. If you want to clear the fractions, you're certainly welcome to, but you're going to get kind of bigger numbers. Maybe if we don't clear the fractions, this might actually be easier to work with. So try to solve this one without clearing the fractions, and we'll actually see it's actually not bad at all. But this one down here, I would definitely want to clear fractions. So take a look at these 2 exercises, about 7 minutes, about 3.5 minutes per exercise. And as usual, as we work our way along, I will jot down a few notes here and there. Okay, so we will touch base in 7 minutes, discuss the answers. Okay, it's right about 7 minutes, so let's come back and touch base. As always with these exercises, if you get a little tripped up somewhere or if you don't complete them, in the amount of time, that's perfectly fine. We're still kind of in the learning phase here. It's not expected that you've mastered these topics completely yet, so don't get discouraged if you didn't get all the way through both of them. If you did get through both of them, great. Um, that's really good for this at this point. Um, or if you made a misstep here or there or needed to look up and get a cue from what I was writing, that's perfectly fine. But uh, try to do it yourself and try to use this as a self-assessment so that you have an idea, uh, how well you're understanding this material. That's really half of the point of these exercises. Kind of half of the point is for you to get practice doing them, doing the problems, but the other half is if you say, oh yeah, I think I understand this material, and then you do two exercises and you can't really replicate it yourself, maybe you don't understand it as well as you thought you did. Or if you say, I think I understand this material, and you're tracking right along with me and you're completing both exercises in the amount of time, then that kind of confirms that you do understand that material and can maybe focus your study somewhere else, for a greater percentage of the time. So, okay. So for this first one, now we could go ahead and clear fractions or decimals. This would have a lowest common denominator of 14 for those denominators 7 and 2, the smallest number that both 7 and 2 go into evenly. And we could do that. We would end up multiplying 2 by 7x minus 14 and 7 by 8x plus 4. We're going to get some big numbers, right? 2 times 7x is 14. 7 times 8x is going to be 56x. So, right, we're going to get some kind of big numbers out of here, but it's not completely unmanageable. However, I want to just remind you that this is a general strategy. It will work for all of these problems. But it's not the only strategy, right? If we see a shortcut, so long as we're being very careful to apply valid equation solving steps and do valid algebraic techniques, if we think we see a shortcut, if we think we see something special about this particular problem, that means if we deviate a little bit from the general strategy, we might save ourselves a lot of time and hassle. We can do that again, so long as we're using valid arithmetic, algebra equation solving steps, things like that. And here we notice that if we simplify both sides first, if I just basically ignore the clear fractions decimals and jump straight to simplifying, I see at least on the left here, this is going to work out really nicely because 7 and 14 are both multiples of 7. That kind of clears my fraction for me automatically. And that actually happens on the right as well, right? So if I see a shortcut, if I notice in a particular problem there's something specific about that problem that lets me leverage that, I can use that. So I'm going to do that here. I'm going to just distribute and simplify on both sides. 1/7 times 7x is just x, minus 1/7 times 14 is 2. So I get x minus 2 on the left. That's pretty darn simple. And on the right, I end up with 4x plus 2. Again, that's really as simple as I can get. So my fractions kind of cleared themselves for me. I didn't have to multiply by 14 and kind of get bigger numbers and then cut those bigger numbers back down at the end of the problem. If I had done that, it wouldn't have been the end of the world. I'd have gotten a fraction at the end that I would have needed to divide out some common factors from the numerator and denominator and got back down to x equals -4/3. Still would have got the right answer, but it would have just been an extra step or two at the end. And in the intermediate steps, I'd have been dealing with slightly bigger numbers. But we see that, again, x minus 2 equals 4x plus 2 is what we simplify down to. And then here I chose to do step 2 in a single step instead of 2 sub-steps. And remember, if you are comfortable with that, go for it. If you're still a little bit shaky, split into 2 steps. Get your x's together first, your variable terms together first, and then isolate your variable term by getting the constant terms on the other side. But here I said, okay, I'm going to move the x over to the right. So I'm going to subtract x off both sides. And then I want to get this plus 2 off of the right side, so I subtract 2 from both sides, leaving me with 3x equals -4. I've isolated the variable term. I'll isolate the variable by dividing by 3. X equals -4/3. Any questions on that one? Okay, and then the next one, this one looks complicated. It looks more complicated, but it's basically just a different way of writing something like this, right? Writing 3x plus 1 all over 9, for instance, is the same as writing 1/9 times 3x plus 1. Right, why is that? Well, just like with a number like 4, I could think of that as 4 over 1 if I really wanted to. With an expression like 3x plus 1, I can think of that as 3x plus 1 over 1 if I really want to. And then I can just multiply across the numerators and denominators, and I see that I just end up back here. So this is really just another way of writing 1/9 times 3x plus 1. So these two expressions are actually quite similar in nature. I mean, slightly different numbers, of course, but the nature of them is quite similar. But here, what I see is if I tried to distribute, say, 1/9 into 3x or into 1, I don't get any nice cancellation. Up here, I got a lot of nice cancellation with these factors of 7 and the factor of 7 that's implicitly in the 14. But not so lucky here. So I will follow the general strategy here. I will clear fractions first, as step 0, I suppose, which involves getting an LCD for 3, 6, and 9. Turns out to be 18, the smallest number that 3, 6, and 9 all go evenly into. I'll multiply both sides by 18, again, being very careful to kind of cordon off the entire left-hand side, both of those terms, and multiply that whole thing by 18. I don't want to accidentally just multiply this 3x plus 1 over 9 by 18 and kind of forget about the 1/6. It needs to get multiplied by the 18 as well. Right? If I had one chunk of stuff plus some more stuff on my left-hand side of my scales, if I say I want 18 times as much stuff on both sides of the scales, I gotta take both amounts of stuff and replicate them 18 times. So the 18 gets distributed into the 3x plus 1 over 9, as well as the 1/6. And here I have 18 times something divided by 9. The common factor of 9 divides out, and I get a 2. Again, if I really wanted to force the issue, I could make that 18 and 18 over 1 if that helps me see things a little more clearly. But I'm left with the factor of 2 still in front of the whole 3x plus 1. So I still have a 2 times parentheses 3x plus 1. 18 times 1/6, just simple arithmetic here, that's just 3, 18 over 6. On the right side, when I multiply by 18, it multiplies this entire 2x minus 3 all over 3. The 18 has a common factor with 3. The 3's divide out, leaving me with 6 that still needs to be distributed into the 2x minus 3. So I'm just being really careful here. There's a lot going on. So I'm only, for each term, I'm only really doing one step at a time. I'm not trying to jump ahead and do 2 or 3 steps in each line. I'm doing kind of one step per line. So on the right-hand side, I distribute my 6 and get 12x minus 18. On the left-hand side, this 18 times 1/6 is 3. And then I have my 2 that still needs to distribute. I'm going to distribute my 2, giving me 6x plus 2. And then the plus 3 and the 12x minus 18 all just come down. My right-hand side is simple. It's fully simplified, 12x minus 18. My left-hand side has 2 constant terms that can come together, making 6x plus 5 equals 12x minus 18. That was an awful lot of work and steps, to get down to where I'm kind of sitting at step one here, right? Where I've completed step one, where I have my equation in standard form, right? In this first exercise, I mean, I had one step essentially to get to standard form, right? So this kind of step zero or 0 and 1 can, I mean, your problem can start in standard form. It can be pretty quick to get there. It can be a lot of steps to just get down to something that's kind of recognizable. But once we get to this point, we say, hey, I recognize that pattern, that form. I'm going to get my variable terms together. I'll subtract 6x from both sides with the idea that that gives me a positive coefficient. If you subtracted 12x from both sides, it's not wrong. It's not going to give you a wrong answer. It's just that you have a negative coefficient, just another negative sign to keep track of. And we'll see when we get to inequalities, that's even a little bit more to think about. So I'm going to get my x's on the right-hand side, which means I need to get my constant terms on the left-hand side. So I need to get rid of this minus 18 by adding 18 to both sides. That leaves me with 6x equals 23. And I divide by 6 to get x equals 23 over 6. 23 is prime. There are no common factors that can divide out here. So we'll leave our answer like this. And if we really wanted to, I guess we could make it, what, 3 and 5/6 if we wanted a mixed number. But I don't see any problem with leaving it as an improper fraction. All right, any questions on these exercises? Okay, so let's work through a couple more examples. The last problem we saw last time was a decimal problem. And we said, well, decimals are kind of like fractions, right? If I have, 3.4, well, I could think of this as 3.4 over 1. Or, well, really, that's 3.4 over 1.0. And if I multiply top and bottom by 10, I can multiply by the same number on the top and bottom. That's just multiplying by 1. It doesn't change anything. 3.4 times 10 moves the decimal point 1 to the right, giving me 34. 1 times 10 on the bottom just gives me 10. I can make my decimals kind of look more like whole numbers by using this trick. Right? I have a ratio of whole numbers now. And especially if I have an equation, I can multiply both sides of the equation by the same number. Maybe it's 2, or maybe it's 14, or maybe it's just the number 10. I see I have 3 decimals, 3 terms that have a decimal factor in them. This has 1 decimal place, this has 1, this has 1. If I multiply both sides by 10, just 10 to the first power, that'll have the effect of shifting all of these decimal points 1 to the right and getting rid of my decimals. Again, I'd rather work with whole numbers or integers than decimals. It's just a little less complexity for me to deal with. So can I clear those decimals in step 0 here? Let me multiply by 10. Let me actually use a square brackets just to make this a little easier to see. I'm taking this entire left-hand side from the 0.2 all the way to the 1.4, putting it in brackets, multiplying that whole thing by 10 just to be clear. And then the right-hand side, same thing. Multiplying that whole right-hand side by 10. On the left-hand side, I see I have 2 terms. Let me go from below here. This 10 needs to distribute into these 2 terms that are connected by this minus sign. That parentheses kind of cordons that 2 minus 3x off. So that minus doesn't create more terms because the 0.2 is still out in front there. Yeah, so a good question. Is it always going to be times 10? So why did we choose to multiply by 10 here? Well, let's look at the right side first. The right side is a little simpler. If I multiply by 10, I see that I have 10 times 2.7. Multiplying 2.7 by 10 has the practical effect of just bumping that decimal point one place to the right, giving me 27 times x minus 1. Now, a little later, we'll take a look at this problem. Well, this problem, give myself a little more room here. Spoiler alert, but this problem has some decimals that where we need to bump the decimal point 2 places to the right to get rid of the decimal. In this case, if I just multiplied 0.25 by 10, I'd still be left with 2.5. I'd still have decimals. I'd actually need to multiply by 100. In other words, 10 squared. I need 2 factors of 10 that I'm multiplying by to bump the decimal point 2 places to the right. This one has 1 decimal point, that decimal place, and this has 0. But I always need to multiply by 10 to the power of the highest number of decimal places. Right, if I multiplied by 10 to the first here, I would successfully clear the decimal from the 0.1, but I'd still be left with decimals in each one of those. I'd have 2.5x and 3.7x. So I need to go a little further, multiply by 10 squared. Yeah, but good question. It's not always 10. It's going to be a power of 10, but the reason we chose just the number 10 here is that we only have 1 decimal point, 1 decimal place at most, and just multiplying by 10 will do the job. Now, if we multiplied by 100, we would also get rid of all the decimals, but then we'd be introducing much larger numbers, right? I don't really want to deal with 270 times x minus 1. That's just going to get unwieldy. Those are just unnecessarily large numbers. Let me actually bump this down just a little bit to get out of the way of my arrows here. All right, on the left side, I have, again, I'm going to take this slowly. I have 10 times 0.2 times 2 minus 3x minus 10 times 1.4. So just doing one step at a time. If I multiply 10 by 0.2, that gives me 2 times 2 minus 3x minus multiplying 10 by 1.4 gives me 14, bumping that decimal point 1 to the right. On the right-hand side, I need to distribute. So I can do that on this step, 27x minus 27. And at this point, I've gotten rid of all of my decimals. I look across my entire equation, there's no decimals left. So I've kind of completed step 0. Now I need to distribute, simplify both sides by combining like terms, and then I'll have completed step 1. Oh, I'm going to be messing up my spacing down here. Okay. So on the left side, I need to distribute. So I have 4 minus 6x minus 14 equals 27x minus 27. Or, well, 4 minus 14 is negative 10. And now step 1 is complete. I've got myself into ax plus b equals cx plus d, where a, b, c, and d are just integers. I'm in standard form. Now I will proceed forward with the goal of combining my variable terms, getting my negative 6x and my 27x terms combined together. I'll do that by adding 6x to both sides. The
How did
other
you
option
get
will be
6?
subtracting 27x from both sides, but that's going to leave a negative coefficient. Where did 6x come from? It came from the 2 multiplying the negative 3x. These two multiplied to give that 6x, that negative 6x.
Sorry, I thought that was a 7.
Which one? Oh, the 3. Oh, yeah. Yeah, sorry. Yep, that is a 3. Okay, so we are getting the 6x on the right side so that we have a positive coefficient. And again, if you want to do this in 2 steps, no problem, but we'll do it in 1 step. I think we're starting to get used to this process. My variable terms are going to end up on the right, so my constant term is going to end up on the left. I need to move this negative 27 to the other side. And I do that by adding 27 to both sides. And on the right, I get 33x. My 27s go away, minus 27 plus 27. On the left, my 6x's go away, and I get 27 minus 10 is 17. I divide both sides by 33. I've isolated my variable term. I isolate the variable now. I notice that 33 is 3 times 11. That's its prime factorization. 17 is prime. No common factors between the numerator and denominator. Nothing to divide out. So that is our answer. And as I always say, you know, on an exam or something, you'd want to go back, plug this in, check. It might be even a bit more cumbersome here because we've got now decimals kind of meshing with fractions. So it might be actually take a little bit of time to check. This might be one that if I was strategizing on an exam, I might say, all right, I'm going to write this answer down. I'm going to maybe put a star beside it or something. I'm not going to check it. I'm going to move on. And if I have time at the end of the exam, if I don't run out of time, then maybe I'll come back and check it later on. I got the answer. I feel like I probably did it right. I haven't checked it, and it's going to be pretty cumbersome to check. So maybe I'll shift gears a little bit here, and instead of, you know, checking it if I'm on an exam where time's a factor, maybe I'll come back to this one if I need to, because it's going to just take a little while to work through all the arithmetic associated with checking whether 17/33 is a correct answer, right? This is just a lot to evaluate when plugging in x equals 17/33. Okay, any questions so far? Let me actually just clean that up. Okay, so 2 more exercises. Again, very similar to the 2 we just did. Take a few minutes to work through these 2. We'll maybe say, we'll look for maybe about 7 minutes still. And again, we'll touch base in 7 minutes. If you have questions in the meantime, you know, feel free to ask in chat. I am going to step away from my computer for just a couple minutes here, but I'll be back in a couple minutes, jot down some notes or answer any questions anybody has. Okay, let's touch base. So there were a couple good questions in the chat. But for the first exercise, we see that for our 4 terms, we have 1 decimal place, then 0, then 1, then 1. So the largest number of decimal places, largest number of places we need to move a decimal point to get rid of the decimals is 1 place. We only need to multiply by 10 to the first. So if I multiply by 10 on each side, again, being careful to kind of cordon off the entire side and multiply the entire thing by 10, I end up with this equation here. I end up with 28x minus 50 equals negative 37x plus 42. I'll choose to add 37x to both sides. And I do that because it keeps my coefficient of x positive. One of the questions in the chat was, well, what if I wanted to move the 28x to the other side? That's perfectly valid. You're going to get an equation that's still a correct equation. But you'll get negative 37x minus 28x. So you'll just have a negative coefficient on the right-hand side. You'll have negative 65x. And then when you move the 42, you'll have equals negative 92. So you just need to be careful with those negative signs, make sure not to leave them off when copying from line to line. Make sure not to leave them off when you're dividing through, things like that. And when we get to inequalities, when you divide through by a negative, you have to flip the inequality. So that's really the main reason that I focus on getting a positive coefficient for x, is when we get to inequalities, it's a little more error prone in equations because you got a bunch of negatives floating around that you could easily forget about. But it's a little more error prone in inequalities because dividing through by that negative, you got to remember one additional thing, which is to flip the inequality. And, I would rather just not have to have one more thing to think about, but it's not incorrect to get a negative coefficient on your x. But we get 65x equals 92 when all of this settles. And then we divide by 65, we get x equals 92 over 65. And here I should check for common factors. I want to write this in simplest form. I note that 65, it's going to have a factor of 5. It's going to be 5 times 13. I noticed that obviously 92 does not have a factor of 5. It doesn't end in a 0 or 5. Does it have a factor of 13? There's not, at least as far as I know, a nice divisibility rule for 13. But I know 13 times 5 is 65. So then 13 times 6 will be 13 more than 65, or 78. 13 times 7 will be 13 more still, or 91. That's not 92, and shortly if I add another 13, I'm above 92. So this has no factor of 13 either in 92. So 65's only factors are 13 and 5. 92 has no factor of 13 and no factor of 5. We are in simplest form. Right? We've divided out any common factors, and we'll write that as our answer. If we wanted to, we could turn it into a mixed number. I don't see really any benefit to doing that here. Correct. If we had done it the other way, we would have, if we had subtracted the 28x onto the right and subtracted 42 onto the left, we'd have got flip-flopped, but we would have got, negative 92 equals negative 65x. Then when we divided, we'd have got negative over negative, which would make a positive. Yep. Yeah, so that's, as long as you track those negatives carefully and, don't miss them copying from line to line and, manage them appropriately, it's, you're still going to get the correct answer. But it is just a little bit more to think about when you have the negative coefficients. Okay, and then our next exercise. Here again, we only see one decimal place anywhere, so we just need to multiply by 10. I multiply 10 into the 0.3 times 1 minus x. The 10 times 0.3 gives me a 3 times 1 minus x. Plus 10 times 6.5 is plus 65. Equals, and here I have 10 times 1.3 is 13 times x plus 1. So I'm combining steps a little bit more here now that we've gone through a few of these problems. But again, you can always You know, if that's a little too much to bite off all at once, you can always chunk it into kind of smaller steps. That's perfectly fine. A little more writing. It takes a little more time, but if it takes 25% more time and you get the answer right on the first shot, rather than having to go back and redo it all over again, that's really a net savings of time, right? I can distribute my 3 to make a 3 minus 3x plus 65, and my 13 to make a 13x plus 13. On my left-hand side, I have 68 minus 3x equals 13x plus 13. As a little side note, one minor thing that I tend to do, if I notice that I'm going to have a negative coefficient, I usually try to rearrange my terms so that the negative turns into a minus. In other words, so I'm avoiding writing negative 3x plus 68. It's a very minor thing. It's not that it's wrong to write it the red way, but I just find for myself when I'm copying down, it's easier for me to miss the negative sign if it's all the way out in front. But if it's in the middle as a minus sign, I'm just less likely to miss it. So, you know, any one of these kind of little things, what does it save you? It's, you know, doesn't save you very much in terms of error rate on an exam or something. But if you recognize, you know, 10 or 20 of these little things, you know, that could be the difference in a letter grade on an exam. So if you notice these little things, especially if you notice places where you're tending to make an error, ask yourself, is there something I can do to make myself less error prone on that step? And, you know, leaving off negatives is a pretty common mistake folks make. So I like to try to embed my negative in between two terms as a subtraction instead. Now, if I had negative 68 minus 3x, I'm kind of stuck. You know, something's got to have a negative at the front. So, you know, it is what it is. Then I'll just, you know, be extra careful. I add 3x to both sides and I subtract 13 from both sides. This gives me 16x on the right, and 68 minus 13 is 55 on the left. I don't know what's with my 5s and 3s today. I feel like they're sloppier than usual. And then I divide by 16 to get x equals 55 over 16. 16 only has factors of 2 in it. It's 2 to the 4th, and 55, an odd number, has no factors of 2 in it. This is in simplest form. Any questions on any of these? So I am seeing good questions pop up in the chat. So kudos to those you know, kind of tracking along and asking questions when you have them. And feel free to use that feature, or you know, if your chat isn't working so great, you can unmute yourself and ask. But you know, I prefer chat just because that way, if folks are focusing on their own work, it's a little less disruptive to them. But if it's easier for you to unmute yourself and ask, you can do that as well. All right, so looking at this next problem, this is the one we kind of previewed a few minutes ago. We see we have 4 terms. This one has 1 decimal place, this one has none. But the 0.25x and the 0.37x actually have 2 decimal places each. So if I just bumped everything 1 decimal place to the right, all of the decimal points 1 decimal place to the right, that 0.25 and that 0.37 would become a 2.5 and a 3.7. We still have decimals. We need to go one more. We need 2 powers of 10 that we're going to multiply by. So I'm going to multiply both sides by 100. I'm going to distribute my 100. 100 times 0.25. That bumps the decimal point 2 to the right. That is 25 times x. Minus, I can think of 0.1 as 0.10. Bump the decimal point 2 to the right. That gives me 10. And of course, 100 times 0.1, 100 times 1/10 is just 10. Similarly, on the right-hand side, 100 times 0.37x, that bumps this decimal point 2 to the right, making a 37x. And 100 times 4 is just 400. Or we can think of 4 as 4.00, bump that decimal point 2 to the right. And I'm in standard form. So steps 0 and 1 have now been accomplished. I'm in standard form. Ax plus b equals cx plus d. I will combine my variable terms, isolate the variable term, and isolate the variable. I'll choose to move the 25x, again, just because that gives me a positive coefficient. That'll put my variable terms on the variable term on the right side. So I want my constant term on the left side. So I'll subtract 400 off to get that 400 off the right side and onto the left side. This nets out to give me 37 minus 25 is 12. X on the right, my 400s go away. On the left, my 25x's go away, and I have negative 410. I've isolated my variable term. I need to isolate the variable. Divide by 12 on both sides, and I get x equals negative 410 over 12. And as always, I look for common factors. I see that they're both even numbers. There's a factor of 2 and 12. There's also a factor of 2 and 410. So what's that going to be? Negative 205 over 6. 205 is not an even number, so it doesn't have a factor of 2. The only other factor in 6 is 3. Is 205 a multiple of 3? Well, remember the trick for 3, for divisibility by 3, is to add the digits together. So 2 plus 0 plus 5, that makes 7. 7 is not divisible by 3, therefore 205 is not divisible by 3. Kind of a funny little trick for divisibility by 3, but that is how it works. So we are now in simplest form. And again, if we really wanted to, for some reason, we could turn this into a mixed number. And, ideally we would go back and check our solution, but we're not going to do either of those steps. Any questions on this one? Okay, so we have, maybe I'll actually leave this one up as a bit of a guide. We have an exercise here. So take about, I think about 3 minutes to solve this one should be plenty. We might even come back in 2.5 minutes or so. So work through this one, come back in a couple minutes and discuss. Okay, let's discuss this one. So for this one, we see that the most number of decimal places we need to move is 2. So we're going to multiply by 10 squared, or 100. And when we do that, multiply out, simplify everything, we end up with this green equation here. Oh, why did that box just disappear? Okay, there we go. We end up with this green equation here. 175x minus 325 equals 100x minus 230. So we're in standard form now. We've completed steps 0 and 1 at this point. And we'll work on isolating the variable term by combining the variable terms together and getting the constant terms on the other side. So I'll subtract 100x from both sides, giving me a positive coefficient, and then add 325 to both sides to get that 325 onto the right side. That gives me 75x equals 95 when all the dust settles. I divide both sides by 75 and I get an initial solution of x equals 95 divided by 75. I notice there's a factor of 5 in numerator and denominator. I can divide that out to get x equals 19/15 as my solution. Any questions on any of this so far? All right, so I think for time considerations, we'll skip this last exercise, and I won't fully solve this one either, but I'll just point something out here that we can multiply by a factor of 10 to say the first or second power to eliminate decimals. If we notice something like this, where I have implicitly a factor of 10, in all of these, 70 is like 10 times 7, 30 is 10 times 3, 100 is 10 squared, or 10 times 10, 20 is 10 times 2, I could actually multiply by 10 to the minus 1 power, or in other words, I could divide both sides by 10, or I could multiply by 1/10. I mean, this seems almost like a bad idea because I just put a fraction in. Why did I do that? Well, because now when I simplify, 1/10 times 70x is 7x minus 3 equals 10x plus 2. These are much nicer numbers to deal with. I noticed that there was a factor of 10 in every one of my terms across the entire equation. Dividing by 10 gave me numbers of a more manageable size, and from here I could go ahead and get my solution pretty quickly, right? The arithmetic of dealing with, 10 minus 7 or negative 3 minus 2 is much easier than dealing with 100x minus 70x or negative 30 minus 20. So I can go the other way as well. There's nothing wrong with that. Most of the time, that's not going to be super helpful, but sometimes you might recognize something like this. Or even if I had recognized that, every term was a multiple of 2 or a multiple of 3 or something, I could divide that out across the entire equation first, make my numbers even smaller to deal with before I started my equation solving steps. Again, if you recognize something like that for a specific problem, it's kind of deviating from the general strategy a little bit, but again, as long as you're applying valid algebraic steps, valid equation solving steps, you're fine to do deviations like that if you see that it helps in a specific problem. And if you think that it would help and you do this, but you end up with, a fraction left over or something, things don't quite cancel out the right way, no problem. Just scratch out that work and go back and do it the general strategy way. No problem there. Just a little bit of time lost, but if it had worked out, then it would have saved quite a bit of time. So, and again, we'll skip over this exercise. This had a similar structure. We could divide a 10 out of both sides and simplify things. Okay, so jumping forward to section 2.6 now, solving a formula for a specific variable. These kind of problems look a lot harder than they actually are. If I notice that I have a formula like this one, I equals PRT, interest equals principal times rate times time, I might be interested. So right now, this is solved for I, right? My variable I, interest, is written in terms of all of the other variables. Interest is isolated by itself. Everything else is on the other side of the equal sign. So if I knew the principal, rate, and time of a loan, I could calculate the interest by plugging in number for P, number for R, number for T, and doing the arithmetic, simplifying it out. But what if I knew the amount of interest I paid, the principal, and the time, and I wanted to find what the rate was? I would need to solve this equation for R in terms of the other variables. So right now, my equation is solved for I, but I want to solve it for R. Well, I noticed that I equals, let me just rewrite this. That's kind of P times T times R, right? Multiplication is commutative. I can swap the order. I can really think of P times T as like being a coefficient for R. This isn't all that unlike saying 3 equals 2R, solve for R. What would I do? I would divide. I noticed that my variable, oops, I wrote solve for X. I'm just so used to writing X, solve for R. I noticed that my variable has a coefficient on it. It only pops up in one place in the equation, so my variable term is isolated. I need to isolate the variable itself by dividing by the coefficient. Well, what's the difference between this example where I have a 3 on the left side as my constant term and a 2 as my coefficient, or this example where I have an I as my constant term on the left side and a PT as my coefficient? There's really no difference. I can just look at this the same way. R is what I'm considering to be kind of the variable here that I want to solve for. And from the perspective of R being the variable, I is like a constant. It's just like some fixed number. So I have a constant term on the left. I have my variable term on the right that's isolated. I've isolated my variable term. It's something times R, my variable. My coefficient of R is just P times T. And to isolate the variable itself, I divide by the coefficient. So on the right, I'm left with R. My coefficient divides out. On the left, I have I divided by PT. So if I knew what my interest was that I paid, what the principal was, and what the time period was, I could compute the interest rate this way. Or if I look at this next example, here I have a formula A equals H times this parentheses, where the parentheses is B1 plus B2 over 2. This would be the formula for the area of a trapezoid, where I have height H and widths, say B1 and B2. So the area of a trapezoid is the height times the average of the widths. So that's what this is. But let's say that I know the area and I know the base widths, the base and the top width, and I want to compute the height. I want to get H in terms of all of the other parameters. So I want to solve for H. But again, I really just say, okay, if H, so I'm thinking of H as my variable, and I'm thinking of all of the other letters basically just being like numbers. So I really have a constant term. This A doesn't have any H's in it. It's a constant term, it's by itself. And on the right-hand side, I just have a variable term. I just have a coefficient, b1 plus b2 over 2. It's a complicated looking coefficient, but it's just a coefficient multiplied by my variable. So if I pretend everything besides h, besides the thing I'm solving for, is just like a number, I really see this as no different than like number equals number times h. It's that same pattern. How do I solve this? Well, I've isolated the variable term. I then isolate the variable itself. I isolate h. Let me erase some of this and just erase all of it. I isolate h by dividing by the coefficient, by dividing by what's multiplied against h. And I do that on both sides. On the right-hand side, I have this thing divided by itself. That goes away. Leave me with just h, the variable that I want to solve for. I've got the variable by itself. I've isolated the variable. And on the left side, I have a divided by this coefficient, b1 plus b2 over 2. Now I have a little bit of arithmetic to take care of. I'm dividing by a fraction, so I invert and multiply. So instead of a divided by b1 plus b2 over 2, I have a times 2 over b1 plus b2. Or maybe I'll simplify that a little further. I can think of this a as an a over 1, and I see this is going to be 2a over b1 plus b2. There's lots of letters floating around, but remember, the letters are just placeholders for numbers. So all of our equation solving steps that we did before, adding the same thing to both sides or dividing both sides by the same thing, they apply to the letters as well. They're just placeholders for numbers. We're applying the same general strategy, right? We have constant term equals variable term. Our variable term has been isolated. Then we isolate the variable itself by dividing by the coefficient, by dividing by all of the stuff that's multiplied on to the variable that's multiplied against h in this case. So exactly the same general strategy. The details look a little different because we have letters instead of numbers floating around, but we just do the same thing for the letters that we would have done for the numbers. Okay, so 2 exercises. The first one should go pretty quickly. Solve d equals rt, distance equals rate times time, for the variable t. To get t equals something where the stuff on the other side of the equal sign has some d's and r's and things in it. And second exercise, a little more challenging. Let's try to solve ax plus b equals cx plus d, our kind of standard form of linear equation for x. Find a general solution, x equals something, in terms of a, b, c, and d. So that if I know the coefficients of my linear equation, I could just match them up and write down the answer. So the second exercise will be a little more challenging. The first one should be kind of a one-step answer. Second one, a little more challenging. So work through these 2 exercises as usual. I'll write up some notes as we go along. And we'll take maybe 7 minutes for this one. The first one should only take a couple minutes, but the second one might take a little more thought and consideration. So about 7 minutes, we will come back and discuss the solutions. Okay, it's a little under 7 minutes, but let's come back and discuss the results here. I didn't see any questions in chat, so that could either mean people really understand this well and weren't having trouble, or it could mean that people are stuck pretty good. So just in case it's the latter, figured we'll come back a little bit sooner and discuss a little bit more thoroughly. So we want to solve d equals RT for t. So we're basically treating t like the variable and kind of thinking of d and r like numbers. So d equals RT is kind of in the number equals number times t format. Or it's kind of in the constant term equals variable term format. Or in other words, we've kind of already isolated the variable term. We've done that, or I guess we haven't done it. It's already done. It's already in that format. So we're starting at the point where we've isolated the variable term. The next step is to isolate the variable itself. So I have something times t equals something. The something is my coefficient. What's multiplying t? What's multiplying the variable? Well, that's just r. In a previous section, it might have been a number like 3 or 2/3 or something, but in this section, that's just r that's multiplying the variable. That's the coefficient r, so I divide by the coefficient on both sides. On the right-hand side, r divided by r times t, well, that's just t. I've flipped sides here as well. And on the other side, I just get d divided by r. That's just d over r. That is just what it is. There's really no simplification I can do here. That is my answer. T equals d over r. If I know the distance that I traveled and the rate that I traveled that distance, I divide those two numbers, d divided by r, and that gives me the time that I was traveling. Any questions on this one? I think it's important to realize that we're following exactly the same strategy, exactly the same steps, just a little bit more abstract because we've got kind of numbers representing, or sorry, variables representing the numbers as well as, or let me say it a little differently. We have letters representing numbers as well as letters representing variables. There's kind of a sense in which all of these are variables, but we're kind of treating t like the variable, and we're kind of treating d and r as if they were just numbers. We're getting them all on the other side. So we're treating d and r kind of like constants, and we're treating t like the variable, so that we can kind of match up terms from our previous discussions. Okay, so what about this next one? This next one's pretty challenging. So if you got this, kudos. If you got a couple steps into it and, didn't quite know what to do, that would be expected. So we're looking to find a general solution for a linear equation like this. We notice that on both sides of the equation, we have a variable term and a constant term. My ax on the left side is my variable term on the left, b is the constant term, and then on the right, cx is the variable term, d is the constant term. I've got my equation in standard form. There's nothing on either side individually that I can do to simplify. So I'll move to my next step, which is isolating the variable term, and I'll split that into two steps here. I'll first start by getting the variable terms together. Here, obviously, we don't have positive and negative numbers, so it doesn't much matter which one we move to the other side. I'll choose to move the cx to the left side. I'll do that by subtracting cx from both sides. That means on the left side, I get ax minus cx plus b. And on the right side, the cx minus cx goes away, and I'm left with just d on the right-hand side. And here I look at this and I say, well, I have ax minus cx. Those are like two variable terms. Can I write them as a single variable term? That's really my goal, to get a single variable term on the left side. And I can by kind of undistributing the x. I notice that ax minus cx is really the same as a minus c times x. By kind of undistributing or factoring out the x, we haven't gotten to factoring proper yet in this course, but we've worked with the distributive property in both directions a bit in 090, and you should have seen this also a bit in 080. So this shouldn't be a completely new concept. So we're not factoring quadratic functions yet or anything like that. That's really what we're going to get into in later on in this course. But factoring something like this, noticing that there is an x in both of these, and I can kind of undistribute that x and pull it out, that gives me a single variable term. It gives me number times x. That's a single variable term. A minus c is just the difference of two numbers. It's just the number itself. Now I have variable term plus constant term equals constant term. I want to get the constant terms on the other side. I do that by subtracting b. And again, I can think of d minus b on the other side as being like the difference between two constant terms, or I could think of d minus b, the entire thing itself, as essentially being its own constant term. So if I think of this as a minus c times x equals d minus b, I have number times x equals number. I've isolated the variable term successfully. Once I have the variable term isolated, my next goal is to isolate the variable itself. And I do that by dividing through by the thing that's multiplying the variable. I want to divide through by the entire a minus c here. And this leaves me with x equals d minus b divided by a minus c. If you had done this a little bit differently, you might have gotten b minus d over c minus a. Does this mean there's two different solutions for every linear equation? Well, no. B minus d times -1 over c minus a times -1. If I multiply top and bottom by -1, I see that gives me d minus b over a minus c. These are just the same equation. Just one, you get from one to the, or sorry, they're the same expression, the same answer. You just get from one to the other by multiplying top and bottom by -1. You don't change the value, it just changes the appearance at a superficial level. Does this mean that every equation has a solution? I mean, wait, I thought we saw that some equations didn't have solutions. Well, not necessarily. Where do we have a problem here? Well, we can see that if A equals C, we'll just put a frowny face, right? Then we're dividing by 0. Strange things happen, we're dividing by 0. If it turns out that A equals C, that's when we end up in one of the two special cases, the identity or contradiction, infinitely many solutions or no solutions. If A equals C and D equals B, then I end up with a 0 over 0 kind of thing. And this is kind of like saying, I have no money and I want to distribute this to no people. How many ways can I do that? A whole bunch. Or if A equals C and D does not equal B, then I have an answer, something like, say, 3 over 0. It's like saying if I have $3 worth of money and I want to distribute it to 0 people, how much does each person get? That doesn't really make sense, right? I can't take an amount of money and distribute it to no people. I can never get rid of my money then. Okay. So we do see both special cases popping up here when A equals C. That's when we get our identity when D equals B as well, or our contradiction when D is not equal to B. This is a little more advanced, this bit that I wrote over here. And just getting the solution is probably on the higher end of the difficulty or the challenge in this section. So this is a more challenging problem. This might be a good problem if you didn't get it this first time through. Note it in your notes and when you go through and you practice some of the homework in 2.6, come back to this problem and see if you take it on fresh after you've gotten a little bit of practice, done some drilling, worked through some of these more abstract problems in 2.6. When you come back, can you get to the solution? Remember that either of these are just two different ways of writing the solution. So if you get either one of them, you've got a valid solution. Any questions on anything from today? Okay, I'll stop the